Hello friends, welcome to e-learning platform of Dr. Bapuji Saranke Institute of Engineering and Technology's Mechanical Engineering Department. I am Sagar Gadkar and I am going to teach you the subject elements of machine design. So in last session we have already started with our second unit, design of joints, levers and offset links, and in this session we will continue with the same. So in this session we will be continuing about the turnbuckle. So turnbuckle or coupler is an adjustable screw joint used to connect two rods which are in tension and which require slight adjustment in length during the assembly. So it consists of a central portion called coupler and two rods. So this central portion is called as coupler. Okay, one side so this is the other side. So this is the other side where the hook is provided, and the other side is also there is an eye. So sometimes on both sides hooks are provided, or on the both sides eye is provided depending upon the application. So one rod has right hand threads while the other rod has left hand threads. The threaded portion of the rods are screwed to the coupler at the two ends. So this is the external threads, and this coupler has internal threads. So one side having right hand threads and other side having left hand threads. As the central coupler rotates, so when this coupler rotates, the rods are either pulled together or pushed apart depending upon the direction of rotation of the coupler. The outer portion of the coupler is given hexagonal shape so that it can be rotated by means of a spanner. Okay, so for rotating of this outer portion, generally we need a spanner. Applications of turnbuckle: it is used in tie rod in overhead crane. It is used in electric poles to support them from the ground. It is used in long telegraph wires. It is used in automobile chassis as an adjustable joint, and it is used in railway track changing mechanisms. So this is the sectional view of the turnbuckle. So in figure you can see this is our coupler. So this portion is the coupler. Okay, the coupler nut, sorry, this is the coupler, and these are the two rods which are subjected to the external loads. Okay, so let's see the terminology. So P is nothing but load carried by the rods. Here we are using one another term, that is PD, which is nothing but the design load and may be given as 1.3 times our given load. Okay, next is diameter. So this is our diameter of the tie rods. So this diameter of the tie rods is given like D is equal to DC upon 0.84. Okay, so this DC is nothing but core diameter. So this is related to threads. So here you need to just remember this DC is nothing but core diameter of the threads, and this DC is calculated as 0.82 times diameter. Okay, next capital D. So this is the capital D, outer diameter of the coupler nut, and by empirical relations it is 1.25 times small d, that is the diameter of the tie rods. Next is D1. So D1, here it is D1, inside diameter of the coupler, and which is nothing but D plus 6 mm. Next is D2, outside diameter of the coupler, and D2 is nothing but 1.5 times diameter. Next is L, that is the length of the coupler between nut, which is equal to 6 times diameter. Next is small l, so this is small l, so small l is equal to length of coupler nut, by relation it is equal to the diameter of the tie rods. T, thickness of coupler, which is equal to 0.75 times D. T1, T1 is equal to thickness of coupler nut, that is 0.5 times D. So this is T1, this portion is T1. Next is small p, which is nothing but pitch of the threads, again it is from the threaded joints. Small n is equal to number of threads per mm length, which is calculated by 1 upon small p, that is pitch. And due to the external load, the stresses induced are sigma t, permissible tensile stress, tau, permissible shear stress, and sigma c, permissible crushing stress for the material. Next is design of turnbuckle. So first step is diameter of the tie rod. As the tie rod is of circular cross section, so in figure this tie rod is of circular cross section and the diameter is taken as core diameter of the thread, that is DC. Then area will be pi by 4 DC square. This DC is nothing but core diameter of the thread. So tensile stress sigma T is calculated as force upon area, that is force is PD. Now here the design load is taken. Okay, remember that for the calculations you have to consider design load, that is PD, and the area will be pi by 4 DC square. So from this equation the core diameter of the threads DC is determined. So here keep in mind the diameter of the tie rod D, that is small d, is taken from the standard table, and for threaded portion the design load, that is PD, design load is considered as 30 times more than the given load, that is 30 times is nothing but 30 times greater than our given load, that is P. Okay, so you have to keep in mind these two notes. Second step is length of the coupler nut. Okay, so the length of the coupler nut is calculated by using the equation tau is equal to design load upon the area. So here the equation of area will be A is nothing but pi DC and L. Okay, so from this equation the length of the coupler nut is determined. Also you have to check the induced crushing stress for the selected dimensions. So by using this equation, that is sigma CR is equal to a design load upon n multiplied by pi by 4 into bracket d square minus dc square multiplied by L. So by using this equation you have to calculate the crushing stress induced and compare this induced crushing stress with permissible crushing stress. Okay, if the induced crushing stress, suppose this value is less than, this value is sigma CR induced, okay, is less than sigma CR permissible, okay, then your design is safe. Okay, next step is outer diameter of the coupler nut. So again for outer diameter of the coupler nut we use the equation sigma T is equal to design load upon area, that is pi by 4 d square minus d square. So from this equation, the outer diameter of the coupler nut, that is capital D, is capital D is determined, but in actual practice D is equal to 1.25 times T. Okay, so here keep in mind, select the maximum value. Okay, suppose from calculation you find the value of D from calculation is, suppose this is 100 mm. Okay, and by using this equation D is equal to 1.25 D, suppose you will get the value, you get the values suppose 125 mm. Then out of these two values you have to select the maximum value. So your diameter of the coupler nut will be 125 mm. Okay, next step is outside diameter of the coupler. So using this equation, sigma T is equal to design load upon area, that is pi by 4 d2 square minus d1 square. You can calculate the outside diameter of the coupler d2. So this d2 is determined, but in actual practice again d2 is equal to 1.5 times T. Okay, so here again you have to select the maximum value for the diameter of the outer diameter of the coupler. So next step is length of the coupler between the nut, which is calculated by L is equal to 6 times diameter. Next step is thickness of the coupler, that is T is equal to 0.75 times D. And last step is thickness of the coupler nut, that is T1 is equal to 0.5 times D. So this is the design procedure of coupler nut. So in this session, if you have any doubt regarding to the design procedure, you can always contact me on this number. Thank you.